What specific problem does your proposed method aim to solve in the context of vision-based dexterous manipulation?
The proposed method aims to address the challenges associated with applying deep reinforcement learning, RL, to vision-based dexterous manipulation tasks, particularly the difficulties in environment modeling, reward design, policy learning, and object perception. Specifically, it tackles the real-to-sim modeling gap by introducing an automated tuning module that calibrates simulator parameters to match real robot behavior, thereby reducing engineering efforts. Additionally, it proposes a novel reward design that disentangles tasks into intermediate contact goals and object goals, facilitating the learning of complex, long-horizon tasks. To enhance policy learning efficiency, the method incorporates techniques such as initializing tasks with human-derived hand poses and breaking down complex tasks into manageable subtasks. Lastly, it addresses the sim-to-real gap in object perception by combining low-dimensional and high-dimensional object representations, ensuring effective transfer of learned policies to real-world applications.
How does the proposed method or algorithm work? Illustrate step by step the main components and techniques you have introduced, including the auto-tuning module, reward design, and policy learning strategies.
The proposed method for applying deep reinforcement learning, RL, to vision-based dexterous manipulation consists of several key components and techniques. First, the auto-tuning module automates the calibration of simulator parameters to match real robot behavior, significantly reducing the manual effort required for real-to-sim modeling. It operates by initializing multiple simulated environments with random parameter combinations, executing calibration sequences, and selecting the parameter set that minimizes tracking error between the simulated and real robot. Next, the reward design is structured around breaking down complex manipulation tasks into intermediate contact goals and object goals. This involves using a novel keypoint-based state representation to specify contact goals, allowing for a more effective reward signal that can guide the RL agent through long-horizon, contact-rich tasks. Finally, the policy learning strategies include initializing tasks with task-aware hand poses collected from human teleoperators, which enhances exploration efficiency, and employing a divide-and-conquer approach to break down complex tasks into simpler subtasks. This allows for training specialized policies for each subtask, which are then distilled into a generalist policy, improving sample efficiency and overall performance in the manipulation tasks. Together, these components create a comprehensive framework for sim-to-real RL and dexterous manipulation.
Can you provide a simple yet illustrative example of how your reward design method works in a specific task, like the bimanual handover? Walk through the main steps involved in setting up the task and how rewards are calculated during policy training.
In the bimanual handover task, our reward design method involves breaking down the task into a sequence of contact goals and object goals. The main steps include 1. Initiating the task with one hand contacting the object, 2. Lifting the object to a position near the other hand, 3. Having the second hand contact the object, and 4. Transferring the object to the final goal position. For each of these steps, we define rewards based on the distance from the fingertips to the desired contact points, contact goals, and the distance from the object's current state to its target state, object goals. Specifically, we use a novel keypoint-based technique to generate contact stickers on the object, which represent desirable contact points, allowing us to calculate the reward by penalizing the distance from the actual fingertip positions to these contact markers. This structured approach enables the RL agent to learn the complex dynamics of the bimanual handover task effectively.
What are the measurable benefits of using your novel techniques, compared to existing methods, in terms of efficiency, accuracy, and the ability to generalize across different tasks and hardware?
The novel techniques introduced in our work significantly enhance efficiency, accuracy, and generalization in vision-based dexterous manipulation tasks. For instance, the auto-tune module accelerates the real-to-sim modeling process, achieving optimal parameter calibration in under 4 minutes, which reduces the manual tuning effort compared to existing methods. Our reward design approach, which disentangles tasks into contact and object goals, allows for the successful learning of complex, long-horizon tasks like bimanual handover with pure reinforcement learning, demonstrating improved task performance over traditional hand-engineered reward systems. Additionally, the divide-and-conquer distillation technique improves sample efficiency by breaking down complex tasks into manageable subtasks, leading to higher success rates in sim-to-real transfer, with our mixed policy achieving a 90% success rate compared to lower rates for other methods. Overall, these techniques collectively enable our system to generalize better across different tasks and hardware, as evidenced by successful zero-shot generalization to out-of-distribution objects and robust performance against perturbations.
How did you validate the effectiveness of your proposed approaches? Please explain the experimental design, datasets, benchmarks, and metrics you used to demonstrate the performance improvements of your method during testing.
To validate the effectiveness of our proposed approaches, we conducted a series of experiments using a Fourier GR1 humanoid robot equipped with multi-fingered hands. We defined 3 dexterous manipulation tasks: grasp and reach, box lift, and bimanual handover, varying object shapes, sizes, and masses to assess generalization and robustness. Each task was evaluated through 10 trials per test object, and we reported average success rates as our primary performance metric, achieving 62.3% for grasp and reach, 80% for box lift, and 52.5% for bimanual handover. Additionally, we performed ablation studies to analyze the impact of specific techniques, such as task-aware hand pose initialization and divide-and-conquer distillation, on training efficiency and sim-to-real transfer success rates. Our results indicated that these techniques significantly improved sample efficiency and overall task performance, demonstrating the effectiveness of our proposed methods.
What are some limitations or challenges you encountered with your method, particularly in relation to sim-to-real transfer, and how do you plan to address them in future work?
One significant limitation encountered with our method is the sim-to-real gap, particularly in dynamics, which we addressed primarily through naive domain randomization. This gap was notably evident in the bimanual handover task, which is the most dynamic among our tasks, leading to lower success rates. Additionally, the lack of reliable hardware for dexterous manipulation constrained our ability to fully leverage the capabilities of multi-fingered robot hands, which do not match human dexterity. In future work, we plan to enhance reward design by integrating stronger human priors, such as task demonstrations from teleoperation, and explore novel techniques to reduce the sim-to-real gap in dynamics. We also aim to extend our framework to more sophisticated robot hand designs to improve the dexterity of our learned policies.